In this video, we're going to talk about related rates. And we're going to calculate related rates in applied contexts. So hopefully you have spent some time learning about some of the different rules for calculating derivatives. What are some of the rules, just to review, for calculating derivatives that we've learned? You've learned about the derivative of the sum of two functions is the sum of the derivatives. The derivative of the difference of two functions is the difference of the derivatives. There's also the product rule, there's the quotient rule, and there's another really important property of derivatives, which is when you want the derivative of a composition of functions. A function of a function, you use the chain rule. Right? And you probably have spent some time practicing applying these rules to calculate derivatives of lots of different functions. And now we're going to apply some of these derivative rules, especially the chain rule, to solving some application problems, some word problems. And this is a specific type of word problem, related rates types of problems. And this is when you have a scenario where one rate of change is related to another rate of change. So remember, kind of the big reason why we care about derivatives in the first place. Why do you learn about derivatives in calculus? Because when you have a function, the derivative is the rate of change of that function. And that's the significance of derivatives. So let's just jump straight to a problem. So it says the radius of a sphere is increasing at a rate of 2 centimeters per second. At the instant when the radius of the sphere is 3 centimeters, what is the rate of change in cubic centimeters per second of the volume of the sphere? So that's a lot of words, and one of the strategies that's helpful in word problems is to draw a picture. So let's make sure we understand what's going on. So there's a sphere. Let's say that's our sphere. And what's going on is the radius of the sphere is increasing. So the sphere, well, here's the radius, say R. R is increasing at a rate of 2 centimeters per second. And what's happening is the volume is also changing. Like as the ball gets bigger, of course the volume, which is the amount of space inside the ball, is going to get bigger also. And the question is saying when, so as the ball expands, eventually the ball is going to be 3 centimeters in radius. And at that moment, if you just stop time for a second, how fast was the volume of the sphere changing? That's the question that is being asked. And so we actually have two rates that are related. If you look back at the question, one of the rates is the rate of change of the radius. The radius is increasing at a rate of 2 centimeters per second. So what does that mean in terms of derivatives? When we think it's increasing at a rate, we think of the derivative, right? It's increasing at a rate of 2 centimeters per second means the rate of change, how quickly the radius is changing, 2 centimeters per second. Well, the rate of change of the radius over time is what we would call the derivative of the radius with respect to time. So this first sentence is saying that dr dt is 2. Okay. And now let's continue reading the sentence. So we're given that dr dt is 2. That's what we know from the first sentence. And then for the second sentence, at the instant when the radius of the sphere is 3 centimeters, so that would be when r is 3. So we're saying when r is 3, what is the rate of change in cubic centimeters per second of the volume of the sphere? So what's another kind of more mathematical way of saying the rate of change of the volume with respect to time? So the rate of change of the radius, right? The derivative is the rate of change. So just as the rate of change of the radius over time is dr dt, the rate of change of the volume is dv dt. So the question is, what is dv dt? So now we've translated this into equations. We're given that dr dt is 2, and the question is, when r is 3, what's dv dt? So the idea is that we know how v and r are related. We know that v is 4/3 pi r cubed. That's the formula for the volume of a sphere. And we want to somehow use the fact that dr dt is 2 and r is 3 to figure out dv dt. And we know this relationship between v and r, this formula, v is 4/3 pi r cubed. So what can we do? See, if you look at the formula, there's no derivatives in it, right? So what can you do to get dv dt to show up and get dr dt to show up? You can take the derivative of each side. So we're going to take the derivative of both sides. We're going to do ddt of the left, v, and then ddt of the right. Well, the derivative of v is just dv dt. Then for the derivative of 4/3 pi r cubed, so we have a constant 4/3 pi that we can move out. That's one of our properties of derivatives. This r cubed, let's think about this. So this r is really a function of time because the radius is changing over time. So when I write r cubed here, what's really going on in terms of the scenario is that you have an r of t that's cubed. And so we have this function, right, r of t. This is the inside function that's being cubed, and we want the derivative of this. So what's the rule that we use? We have an inside function and an outside function. For the composition and the functions, we use the chain rule. So we're going to take the derivative of the outside function. So we're going to get 3 times, and then the inside, r of t squared. And then we have to multiply by the derivative of the inside. Well, the inside was r of t, so the derivative is dr dt. Okay, that's an important step to use the chain rule here. And now we have our equation. Do you see how this equation has dv dt in it? dv dt is here. My r of t, I'm just going to, again, abbreviate this to just r, because if you write out r of t, it just kind of clutters everything. So I'm just going to write it as r, and then times dr dt. So now I have a dv dt here, my r here, and my dr dt there. And that's exactly what we want, because we know now that since dr dt is 2, r is 3, and we're looking for dv dt, what are we going to do? We're going to substitute the things that we know into this equation, because we're trying to find dv dt, and we know r and we know dr dt, because the problem tells us that r is 3 and dr dt is 2. So dv dt is, well, when you calculate this, let's see, the 3's are going to cancel here, so you're going to get 24 pi. Is that right? There's a 3r squared. So 72 pi. And the question is, what's the rate of change in centimeters cubed per second of the volume of the sphere? The answer is 72 pi. So what's going on is the volume of the sphere is increasing at a rate of 72 pi cubed, 72 pi cubic centimeters per second. That's the interpretation of this 72 pi. Okay, so there's a lot going on. This is definitely a different type of problem that you might be used to. So let's practice. So if you think about the solution, let's discuss how would the answer change if the question asks for dv dt when r is 5. So basically, if you look at this question, let's say that this 3 was 5. Let's just pretend. And you had everything stay the same. What would be different? Which steps would be different? Well, if you think about it, the only place where you use the radius of the sphere is at the end when you plug stuff in. So the only difference is that you would have a 5 here, but all the steps are the same. So you would get, let's see, 25. You would get 200 pi. So you would get 4/3 pi times 3 times 5 squared times 2, and then that would be 200 pi. Okay, we have time for another question that's sort of related but a little different. The volume of another sphere is increasing at a rate of 24 cubic centimeters. When the radius of the sphere is 2, how quickly is the radius changing? Well, this time, what we're given how fast the volume is increasing. So dv dt is 24, and we're given that the radius, when the radius is 2, we want to know how quickly the radius is changing. So what is dr dt? So when r is 2, what's dr dt? Now the when part is important because what's going on is that this sphere is changing in size. And it's just saying when the sphere is 2 centimeters in radius, then how fast is the radius changing? It's not like the sphere is just always a radius of 2. Okay. Well, it's the same kind of thing. We're going to get the exact same equation. We use the exact same equation that relates dv dt and dr dt. It's dv dt is, actually, if you look back at the equation, 4/3 pi times 3r squared dr dt, we could have actually just canceled out the 3's. And then we would get 4 pi r squared dr dt. The only difference now is we need to substitute the dv dt in here. So 24 equals 4 pi times r is 2 squared, and then what's dr dt? So we get 24 equals, so you get 2 squared is 4, and then 4 times 4 pi is 16 pi. dr dt and now you divide both sides by 16 pi, so dr dt is 24 over 16 pi. And then we can just simplify that. Let's just divide both sides by 8. So it's 3 over 2 pi. So this question is asking, let's make sure, though, that we don't just, circle this and call it a day, because the question was asking, how quickly is the radius changing, right? So, 3 over 2 pi, if someone had just asked you how fast is the radius changing, and you just say 3 over 2 pi, that doesn't make any sense, right? We want to say that it's increasing, so we would write out the radius is increasing at a rate of 3 over 2 pi. Now we need units, centimeters per second. 24 cubic centimeters per second, sorry. 3 over 2 pi centimeters per second.